right, so let's start. We are on the second step of distributed query processing methodology. That's data localization. And we had started on that one. We had seen that it's a module that it takes in the query that has come in from the decomposition. The query still works on global relations, and we use we take into consideration the fragment schema, right? We compare what the incoming query is talking about. It's talking about global relations, yes, but we know that you not stored those ones. We stored fragments. So we are converting a global relations query into a fragment query. That's basically what we're doing. It's all we're doing. When you have a query that says select star from invoices, we want to transform that into fragments. So it says select star from invoices 2, for example. And you know that the queries can come when they are complex, they have joins and so on, but you want to now transform it into a fragment query. And we don't want to fetch fragments that are not going to be used to answer the query. We want to only fetch those that are necessary. For us to do that, we, for a number of steps, we replace the global relations, the global tables with their reconstructions. And that's why you remember when you are doing the beginning of the class, you're saying that when you fragment a table, there must be a mechanism to reconstruct. Now it's coming into place. You need to reconstruct the invoices table from its fragments. You want to use a fragment to reconstruct the invoices table. It's the first step. When you do the reconstruction or the equivalent of that table, but now in terms of fragments, we decide which ones are not going to have to be used. We check based on the fragmentation information. Based on what the query is asking, which fragments are not going to have the data that we want, either the records that we want or the columns that we want. We ignore them and are only left with the fragments that are going to answer the query. We prefer to have it as a tree format. The leaf, the lower you go, the earlier you start. The execution starts from the bottom up. You prefer to start with the joins as opposed to unions, because joins sort of help us to reduce what you're transporting, what we are shipping. Okay. Also, the joins also help us to see further which fragments, once they're joined, will have empty relations, and therefore we don't need to ship fragments just so that we can join them later and find that they don't have any records that come out of them. Yes, so like on the left, the top left, we have the incoming query from the user. It is decomposed. There's normalization, analysis, and so on. We end up getting a fragment. I mean, an algebraic query, and that algebraic query can be as a tree, as shown at the bottom. And that's but to bottom left is the input to our data localization program, which is like this. It is talking about global relations, EMP. In this case, it is a select star from EMP employees global relations using that filter. So we transform this EMP. We reconstruct. We replace it with a reconstruction, which is a union of all these three relations. That's a reconstruction. After that reconstruction, then we remove useless fragments based on the query that is coming in. The query is saying we need to filter for this data. Employee number is equal to E5. From our fragment schema, top right, we can tell what records are in which fragments. Employee 2 is where we'll find records that satisfy that filter. Therefore, we can get rid of the other fragments from the reconstruction. We don't need to ship them from wherever they are to the control site. Only to do a union, and then we filter the records out. And therefore, the output of the localization program is what is at the bottom left. So this is the output of data localizer. The localizer will end up giving this as an output. That's what we do. Simple query. Yeah, but of course, we have complex queries. We have those that have joins. We have those that are talking about vertical fragmentation. The same procedure happens. Okay. In this example, we have this as an input, the middle left. We have replaced the assignment table with its reconstruction, which is the union of assignment 1 and 2. We'll do the same case. We replace EMP with its reconstruction, which is the, since a horizontal fragmentation thing, we replace with the union. This. So the code is just asking for all records from employees in a join assignments on that expression. Employee number is equal to assignment with employee number. And you have the fragment schema below. We know that assignments has this fragmentation with those kinds of records, and employee has records that look like that with those filters. And we can automate this process. The localizer is able to see, to compare these filters. These are filters, these are predicates. You can therefore compare those predicates and they return true or false. The filters are predicates. So these predicates, if you apply them to some logic, you can tell which ones are going to have false and true. Therefore, we can tell that from the second step of this localizer, where we are replacing the unions and the table to their reconstruction, and then to join them later, we can join them first before shipping them to do union. We join them. What you're calling, we distribute the joins of the unions. We do a permutation for the possible joins first. So we can take employee 1 fragment. It can be used to join with all the assignments fragments. So employee 1 is joined with assignment 1. It's also joined with assignments 2. Then employee 2 is joined with assignment 1, followed by 2, and likewise. So we do all possible scenarios. When you do those possible scenarios, we check the fragment schema. We can tell which joins are going to have empty relations from the filter that we've just seen in the previous slide. We can therefore see that because assignment 1 has employee numbers less than E3, okay, then with that fragment can only have the records when it's joined with employee 1 and no other employee fragment. Therefore, wherever you have assignment 1 and any other employee, you can already know that we will have no data coming out of that. And when we use that criteria, we end up with the following fragment tree. Yeah. The following fragment tree, fragment query. Because we have distributed the joins of a union, right? So these ones will give us some data. We join this one, then we union later, perform the union later. Okay. And this is the output of that data localizer. That's what it will ship down to the next stage of the distributed query processing methodology, which is a global query optimization. Let's take an example of vertical fragmentation. We have a query, the bottom left, that goes to the query decomposer, select employee name from emp. In this case, employee was fragmented vertically, and you can tell that because with this fragment schema, the middle left, we have 2 fragments, emp1 and emp2. emp1 has the name, and emp2 has a title. Okay. So what do? We replace the relation emp, where it's saying select employee name from emp, with the reconstruction of emp. This is the reconstruction of the employee, right? emp1, emp2, emp1 join emp2, that's a reconstruction. That's the first stage. It's just mapping, replacing emp with the reconstruction. Then the localizer checks which fragment has what we need. emp1 has, from the fragment schema, emp1 has 2 fields, the primary key and the employee name. emp2 has 2 fields, primary key and the title. Therefore, emp2 is not necessary in answering our query. We don't need to ship it, only to drop it out because it doesn't have the column that we want. And therefore, we end up with this output as our fragment query. So the localizer gives us that as output. When you have the derived horizontal fragmentation, now you have the same principle applied. Replace the query, the incoming query, the global relations with the reconstruction. Assignment has this kind of reconstruction. Employee has this kind of reconstruction. Then there's a filter, right? And once you have this replacement, you can now tell, because these two tables have been fragmented using DHF, you can tell the owner of the link. So there's an owner and a member. The owner of the link is employee. Why? Because we have done PHF on employee. DHF is done on assignments. Okay. Now the incoming coding is filtering for title is equal to mechanical engineer. You can already tell which fragment of employee will answer our query. It is which one? It is employee 2, because employee 1 only has programmer records, and you're looking for mechanical engineer. So employee 2 will answer our query. You can therefore get rid of the fragment already, employee 2, and get rid of it. Then we know that assignments was fragmented using DHF. And DHF, the fragment, it follows primary key, foreign key thing. If you have gotten rid of employee 1, you should also get rid of assignment 1, because assignment 1 only has records relating to employee 1, which are programmers only. And therefore, we'll be left with employee 2 and assignment 2. Yes, that's so this one illustrates what we've done. The top left, we have removed employee 1. Then we remember, you usually want to send the joins down, bring the joins first down and bring it up. But when you bring the joins down, we know that employee 2 only joins with them assignment 2. Yeah. So we know that we have gotten rid of employee 1 because it doesn't have that data. If we try to join employee assignment 1 and employee 2, we will get no data. Why? Assignment 1 is a derived fragment of employee 1. So this will give us an empty relation. We are therefore left with only the join of assignment 2 and employee 2, which is what we have on our bottom left. And the bottom left is the output of our data localizer. Yeah, so the data localizer, you can automate this. So you just need to have a way to understand the fragment schema, and when the query comes in, you can tell which fragments are going to be useful in answering the query. Those that are not, you get rid of them, and you have a fragment query from the global relations query. Yes. Hybrid fragmentation, same principle. Yes. So you can consider the PHF where there are filters. Remove empty relations that will not have records because of the filter that you have. The incoming query has a filter. You've replaced the global relations with the unions, right? Then you can knock off the fragments that don't have data. Yeah. Same. Then go to vertical fragmentation. Remove fragments that don't have the queries that you need. Don't have the attributes that you need. Once you've done that, then you push down the joins so they're down. And they're done fast. You can get rid of some fragments also because they might give you empty relations. So when you follow those 3 steps, then your localization is complete. Yeah, and then there's a diagram to illustrate that. The top left is our fragment schema. Then you have the incoming query. The first thing you do is to do what? Is to replace the global relation with the reconstruction. This is hybrid. It's a combination of two horizontal fragments and two larger vertical fragments. Then you know that the data based on the filter and the column that you are looking for. Your filter is employing employees who have E5, and E5 is only available in employee 2. Yes. So employee 1 disappears, it has no records. Employee 3 is all records, but only the primary key, employee number, and the field title. We're not looking for title, we're just looking for employee name. And we end up with the bottom, the top right, as our fragment query. Yeah, and it is in algebraic format. Okay. Yeah, so the decomposition can happen even in a centralized database. We saw that the decomposition, do the analysis, in normalization analysis, and the structuring and so on. But the localization only happens when you have distribution. Why is that? Because you're taking a query on global relations and converting it to a fragment schema, to a fragment query. So fragment queries don't exist in centralized databases, they only exist in distributed databases. Yeah. Right. So any question about data localization? So if there are none, let me go to the next topic, which is the third step of our distributed query processing methodology, and I'll start a new recording for this. Yes, we have. Yes. All right. Having done data localization, we have fragment queries working on fragments, and you know that these fragments are sitting all over the distributed system. We need to get data from them. The easiest way to get data is to ask the sites to give you the fragments, then at the central site or the decision site, or the site where you've accepted the incoming query from the user application is, and you do the filtering and joining there. As much as that may look simple, it consumes a lot of network resources. And in our system, because we're distributed, our biggest cost is really the transport cost. Yeah. So when you ship entire fragments to the central site, then it's not very efficient. Even though you have localized the query, and therefore you are only shipping fragments that are going to answer the query, and you're leaving out those ones, even though they are part of the table, that are not being used in answering the query. Of course, that's more efficient. You didn't ship the entire reconstruction or the fragments for our table. You didn't ship that. You're shipping only maybe 1 out of 3 fragments from a table, and maybe 2 fragments from another table because they're going to be used to answer the query. It is still expensive in terms of transport. And there's an opportunity for us to do just a bit more optimization rather than having all data sent to the decision site from the different sites where those fragments are, we can have, if you can study the execution strategy and come up with a number of them, and we calculate the cost, and the cost mostly is bandwidth, is the transport cost, there's an opportunity for us to choose a strategy that is cheaper for us. Rather than having that central site receiving everything, there could be an opportunity for us to do some intermediate processing, send a fragment to a site that contains a related fragment, maybe send the smaller fragment, maybe it's part of the owner of a link to place where the name of the link that has the child record, child fragment records there. It comes to this site, you end up processing, do some small processing, we reduce the records that survive that join. Then this data is sent again to a related to a site that has a related fragment. We do some more processing, we end up with smaller records, fewer records, which we then ship to the decision site. We end up shipping. The total cost in terms of what you have shipped is much less than compared to the first one where we are shipping the entire set of fragments. Remember, we usually ship the entire fragment unless we have a filter that we can already filter locally in the site. We ship everything. Yes, so the transport cost is cheaper. The total transport cost is cheaper in the second scenario. If these strategies that can reduce, you might find scenarios where even having intermediate processing may not really assist you, and it is consuming time, right? And it's probably better to just have ship everything to the central site in terms of speed and and transport cost. But we want to do optimization, consider lots of strategies, maybe not do an exhaustive search, maybe a heuristic search, so that we end up reducing the cost, the total cost in our system. Yes, so that's what we want to look at today, the global query optimization step, which is the third step in our distributed query processing methodology. The input is a fragment query. It's no longer a global query, the global table. Now you're already in fragments, talking about fragments. The data localizer has done some bit of elimination of fragments that will not be used to answer the query. So you just have a set of fragments that are necessary in answering the query. But because our system is large, it's distributed, we want to further reduce cost. We want to optimize that query. And the input is a fragment query, but we also use statistics on fragments. How big are the fragments? Which ones are related to which ones? And possibly also what was the cost in us transmitting those fragments the last time? When we did intermediate relations, how many survived? How many records ended up being shipped the last time we did it? Statistics on fragments. Yes, just a reminder on query processing. We know that the optimizer wants to minimize the cost, and cost can be in terms of time, processing time, and also network, and also response time. When you do things in parallel, the response time reduces as opposed to doing them in a longitudinal fashion, in a sequential fashion. For our case, the data transfer is the biggest cost. The CPU cost, which is a fact, input-output, but we find because of limited bandwidth and the distance in terms of distribution, we consider transfer time, transfer cost as the biggest cost. When you have a cost model, cost models that we see, we'll be considering the transport cost mostly. We will ignore the CPU and IO. Yeah. When you have a chance to do some things in parallel, we also consider response time. Yeah. So if you're writing an optimization algorithm, you need to have a cost model. How do you cost the thing, right? What is the weight? you might have y is equal to, maybe you want to assign a cost, a unit. Maybe it is 10 units per record. So if you have 10 records, you have 10 units of cost. But then there could be some setup cost, right? Because of latency, because of any whatever it is, the cost that is definitely there. Then if you have few records, right? So you need to see to figure out what are the weights. The bigger the distance that your system covers, then maybe the bigger the setup time, the cost, and also the bigger the weight for the per record, right? But if you have a big bandwidth, maybe you have very fast internet, then the cost per record may be less, but there could be some setup time because you are still far apart. Your system is working across continents. You also consider search space. What are the different ways you can execute a query? If it's a simple query, select star from invoices. The search space is so small, you're only going to ship, but there's only one option, just ship all the fragments to the central site. But when you have queries that talk about maybe 2, 3, 4, 5 tables being joined somehow filters, then your search space starts to become bigger. There are many ways you can execute that query. There are many ways you can ship fragments from one site to another site at a different costs. Yeah, so when you choose one strategy within your search space, you can apply the cost model we just talked about to see how expensive is it. So you can have your search space, you can have the first way, maybe ship everything to the central site, then you apply the cost model. If there are 3 fragments, fragment 1 has 5 records, you apply 10 is equal to 10x, y is equal to 10x plus c. 5 records times 10 is 50. Maybe the setup time is 10, so that's becomes 60. So 60, and you have 3 fragments, you end up with some kind of cost. If you ship some fragments to a site first before they now ship everything to the central site, it might be cheaper. So like that, you continue like that. The different strategies that you might have, you end up with some kind of some graph within that search space. So this becomes like your search space. You want to have a solution where you have the least cost, somewhere like there. And as you're generating the different scenarios within your search space, that takes time also. That prediction takes time. Do you want to spend time predicting it, or you want to just ship everything at once and improve on the response time? Then how to move within this search space? How to generate these different options? The first option was like moving everything to the central site. Another option was to maybe move only one table to one site, and after that, everything else come to that different site. How do you do that? How do you navigate? Well, that also it's part of how you'll get to the lowest values quickly. Yeah, how do you navigate? If you do an exhaustive search, how do you get all the results or the possible ways in the search space? Then there's some concepts you need to remind yourself when predicting or estimating. Let's say estimating the costs that will assign in the search space for each possible strategy. Yeah, selectivity factor. Selectivity factor, you saw that in the query optimization, in the query processing video. And here there's some of you were not able to see that video, so I'll check the technical problem for that. A selectivity factor, it simply means if you have a table that has data and there's a query coming in that says select star from cost units. It's an SMI system from cost units, and the cost code is S3 3103. So the selectivity factor just tries to see what you have put as a filter versus what are the possible units that you can ever have. Yeah, so you're asking for one record across a possible maybe 48 units, right? 1 over the number of values in that domain. If you are listing the courses, it's very simple course code, maybe A, B, C up to Z, you can only have 26 courses. And if the query is saying select stuff from courses are between A and C, means we are asking for three records out of the possible set of 26. Now you may not have the 26 courses there already. Maybe so far you only have 10 or 11 courses. But you see, when you're an optimizer, you may not know exactly how many records are in the table. So you try to see the possible records that are there. You can only have 26. So if this query is coming in, I know the query is coming in asking for 3 values. I don't know how many records are in the table. Yes, but I know the maximum number that can ever be contained there. So I estimate somehow that it is 3 or 26. That's a selectivity factor for that. You're asking for 3 out of a possible 26. So you are likely to get 3 or 26 records, even if there may be, even if you don't know the actual number of records that are there. So, but it's an estimate, right? It's an estimate. If you're looking for one value, maybe for one course, it's one value, right? If it's a range of values, maybe it's more than select stuff from courses where the course code is K and above. So you check, you can have 26 values out of minus up to K. You don't know what the ASCII value for K is, somewhere there. So 26 minus that value, yeah. Divide by 26 minus 0, which is 26 really. Yes, so you have that kind of thing. So there's some brackets there, right? It's an estimate. Yes, then when you have more complex predicates, maybe select stuff from course code, from courses where the course is between A and K, and also the course is maybe between H and U. That's combining. You start talking about, start now thinking about the probability, your statistics and probability, right? When you're combining two predicates, the likelihood is a product of the two likelihoods, right? When it's a disjunction, then it's a likelihood of is an addition of the two likelihoods, but of course you have to subtract the likelihood of where both of them are intersecting are the same, right? That one, yeah, you think about it in terms of statistics and probability. Yes, when you talk about a set of values is the same as the first one. For example, if you're saying select stuff from courses where course code is B, the course code is in a set B, C, and K. Those are 3 values, so it is the same as 3 divided by 26. Right, so you need to be aware of this cost estimate in terms of records. Now, in terms of projection, you need to be aware that when you're projecting some columns from a relation R, the number of records you'll get from that projection, if you're saying select employee name from employees, is the same number of records that you get of the entire table size. If the table has 10 records, when you're projecting just one column, you still end up with 10 records, right? Still end up with 10 records. Why do you need to know that? Of course, it's obvious, but when you're estimating the size and your cost model, you're only considering records as opposed to records and columns. It will be more accurate, but it will be too complex to estimate. If your y is equal to 10x plus c formula only talks about records, then you need to remember that when you're selecting, when you're projecting a column, you still end up with the same number of records as the same number of records in that table. When you have a cross join, when two tables are going to be cross joined, then the resulting number of records is a product of those of the records of two tables. So you're saying select start from employee cross join cities. If you want to see if you have to have the employees work in all the cities at some point, then it's as many cities as you have employees, the product of the cities and the employees. For joining, if you have two tables, select start from invoices in adjoin invoice details. Yeah, invoices has 5 records, invoice details has 18 records, and you are doing a join there. You need to know when you're estimating the cost. Let's assume we want to do this join and then ship the records to another site. These records are in one site. You don't know how many records are going to be in this shipping packet. The number of records of that join is the same, but you have to check which is the primary key. If A is a key in R and B is foreign in key in S, like in this case, invoices has a primary key, and invoice details is a foreign key, has a foreign key. You get how many records here? You can get 18 records coming out. But if it was the other way around, if the table on the right, if you can call this R and S, if S is a primary key, such that it is like this, let me just draw it again. If it's like this, R and S, if S is a primary key and R has a foreign key, S is a master table or the owner of the link, R is a child table. You have invoices here, and R is the details, invoice details. Maybe some invoices didn't have details. You do an inner join, select start from invoices, inner join details on invoice ID is equal to details at invoice ID. And you had 18 invoices, and you had 5 invoice details. How many records will you have being shipped out? It will be 5 records. Yeah, so you need to understand and know these things when you're estimating the cost. Yeah, you're navigating your search space. So for each possible strategy, you put a cost. You need to know that. Okay. And why do you need to know that? For example, if these two, there are fragments and they're in different sites, you might want to ship the table that has the fewer records to the place where the records are many. Then you do a join. Then you want to estimate what will come out of that site to be shipped to the central site. You need to know it is 18 or 5. You need to be sure. Okay. When you have union, and you want to do a union with 2 fragments, maybe there are horizontal fragments done with PHF. You need to know that the number of records is a range between the number of records in one table and number of records in the other table. The upper bound is the 2 tables combined. Maybe the first one was invoices 1, and the other one is invoices 2. Into a union, the first one had 7, the other one had 10. The records we get after that union is can only be 17, maximum of 17, and a minimum of 10. It can be between 10 and 17. Of course, if you have done proper PHF, then it's sure to be 17, because it can only be less than 17 if there are some duplicate records. And you've seen that when you do proper fragmentation, proper PHF, you should not have any duplicates. Otherwise, you will negate the correctness properties of fragmentation. But in real life, if you're going to do union of 2 tables, you should expect that it can either be 10 records or 17. Okay. Yeah, that's it about estimation. Now, in terms of navigating the search space, deciding how to get strategy 1 up to N, the different ways you can combine your relations, fragments. Yeah, I'm putting just relations because whether it's a fragment or relation, this step for communication, it doesn't really care. Yeah, just that we're getting them from the localizer as fragments, but the optimizer, it knows that these are relations. If you have this kind of query, select employee name, responsibility from employee assignments and projects, when they're joined like that. Yeah, there are many ways you can join those tables to get a result, the same result. You can start with the bottom left. Yeah, you can begin by joining assignment and project. They're related, so you can join them with project number. Then whatever you get from there, you join with employees. That will answer the query. You can also do that middle part there. You can start with assignments and employees. They are related because they have a key called employee number. Whatever you get from there, you join with projects. It will also answer the query. These are different strategies. What that would mean in the distributed systems site example is that you have those 3 sites. One has employees, the other one has assignments, the other one has projects. For the first strategy, you are joining assignments and projects. So you can say whenever you have a tree phase like that, it means you shift the left item to the one on the right and do a join. So you move assignment to this guy. So this one means you move assignments to the site where where project is. Sorry. So you move assignment to where project is. Do a join. Whatever comes out of there, you move it to employees. This is the first strategy, this one. The second strategy is you have those 3 sites. Assignment, employees, and project. You are moving, again, you're moving assignments to where employees is. No, you're moving assignments to where employees is. You join the employees and assignment. Whatever you get out of there, you ship to projects and join there. Right? Depending on how big these relations are, you get different costs. Yeah. If assignment is so big, okay, now either scenario you're moving assignment. But if employees they are smaller, much smaller than projects are, then it means that the second strategy might be more expensive or cheaper, right? Maybe more expensive or cheaper. Yeah, there's also a third one, that bottom right. We are saying you move project to where employees is and do a cross join. We know cross joins have very many records, and move those records to where assignments is. That one would be a very costly strategy. So if I can draw a search space, let me just do something here on top. We have those 3 strategies. The first one can be at costly. The second one can be much cheaper. But the third one is very, very costly. It's much higher. So you can have this kind of graph. Yeah. And there are also other ways. You can start with you can do employees shipped where assignment is. Yeah. You can have this space here. Let me just erase these ones. You can have another strategy that says you move employee you start with employee and then you join it with assignments. Now, the way I've joined the assignment, you combine it with projects. And that. So now when you have few employees and you ship the employees to the assignments, the employees are maybe fewer than the assignments. You have saved on that first shipment. Then the shipment of the join between employees and assignments shipped to projects, then you might end up with a very efficient, that could be the lowest cost, right? So that's how you navigate through the search space. You need to find out, the different combinations. When you have lots of relations that you need to join, you could decide to have the shipments done in parallel, right? How many tables? Like if you look at the bottom right, this bushy tree, R1 is moving to R2, and at the same time, the R4 is moving to R3. You can have those things happening in parallel, right? You can check for possible parallel transmissions, or you can restrict yourself to having only one transmission at a time, then combining it with a left deep tree, or you can just have a deep tree. So you need to have decide which one to use, right? So you can create your search space, but you want to now get the lowest cost. Then how do you navigate to the search space? When you have gotten the first possible way, how do you navigate to the next one? We started with this guy. How to generate this at a second cost? Is it random? If I go back to this page here, let's assume that you've decided that this is the first strategy. How do you go to the next one? How do you decide, okay, now that we moved R1 to R2, and then the result to R3 to R4, how do we go to the next one? Do we replace the leaf nodes first? Once you replace that, then you replace the next upper level, bring it down. How do you navigate? What do you interchange? Is it random? Do you just randomize and say you want to randomly assign these spaces in the tree, whatever relation it is, or is it guided? Is it randomized, or is it deterministic? Right? If you do that, if it's random, it means you might have some costs that they can be very random or very erratic. If it is deterministic, it means that you'll end up with a graph that's sort of not so random, but it sort of has some kind of predictability, right? Now, if you think about it from an optimization, a classical optimization problem, if it is sort of deterministic, you can use those algorithms that you are aware of for optimization, even for neural networks. They have a way of adjusting the weights and so on, so you can achieve optimal results, and you remember them very well. Yeah, there are those that simulate something falling. If it's falling, it increases speed. It tries to still manage to go up. The small crescents, it manages. It continues having some momentum, right? There are all those. There's those that say that you should be even do it randomized, but reduce the randomness as you proceed, as you progress, right? And then you pick the minima, get some good minima. They may not be the best, but it's an optimal minimum. Yes, so now it becomes an optimization problem, especially when you have lots of relations to deal with. Like this, and a deterministic one, you first take two relations, then you join the third one like that, and you increment. Otherwise, you have the whole thing. You just say, okay, this slot should have these relations that are assigned at random, and you just get. So for each one, you calculate the cost. You get the cost for this randomized thing. Then this one, and as you plot your search space. And then you try to get a global minima or just have a good cost. Yes. Then when you're joining, how do you get the cost of join? Let's assume you've taken one strategy and you want to take on one strategy. Okay, this particular thing is cost. These are different strategies. You picked one strategy. How do you get the cost? How do you determine what cost? Yeah, we are joining these relations, and we are transmitting them. Remember, you are transmitting them. If you have this kind of tree that you want to estimate for, it involves shipping this relation R1 to where R2 is. So when you ship them, if you have to calculate the total cost, transmission, local cost, everything, there's the shipping cost, of course. Once you ship it there to the other side, you might need to store it if it's too big. Usually when you ship the child tables, they are usually assumed to be very large. You have to store them. The cost of storage is the cost of joining them, then there's a cost of sending them across. If you're sending the master or the primary table, it's normally assumed not to be so big compared to the child table, right? If you're sending invoices, there won't be so as many invoices as there are details. So if you're shipping the primary table, you might not need to store it. It's already in RAM, right? So there's no cost of storing. So you estimate the cost for joins using that kind of assumption. You might use nested loops to join. You might use merge joins, and these are things that happen in local databases. But remember, we said that for us, when we are talking about distributed databases, we will assume all those local costs are zero. It's just a transport cost. However, we need to know the outcome, the number of records that are the outcome of that join. Yes. Then, if you recall from your query processing, there was a concept of semi-joins. Remember semi-joins, where you're saying that yes, you have these two tables that are related, master data, invoice and invoice details. So invoices, rather than ship the whole invoice fragment or table, let's just ship the
Greg, usimwambie amedrop off so that maybe asikuwe anajiongelesha.
Acha nimcall, acha nimtext.
I got disconnected. Were we on this slide? Let me display it again. Well, are we here? Okay, it's only a few seconds. Yes, so I think I was talking about this previous one. I was saying you need to know the primary keys, the primary tables, the foreign keys, and the child tables. Yeah, so that you can know the cost of performing a join. Okay. Determine the best join ordering. Of course, it also has a role to play, like I was showing in the previous examples. You have the tree, the table on the left. You can assume that that's the table that you ship. to join with the one on the right, which has an implication on join ordering. You basically want, the rule of thumb is that you want to ship tables, a table or relation to a site where another relation is, and that relation is related to whatever you're sending to avoid cross joins. Remember cross joins. Cross joins, you use them in scenarios where you need to combine two tables so you can ship the one combined relation. Normally want to send one relation when those two tables are not related. For example, you can have in the student database, you can have if you have a table for students and a table for trying to for a table that is not related to students. Let's say you have a table for exam type, first attempt, special, soup, and so on. So there's no direct link between these two tables. It's not there. So those two tables are not related. So to ship them, if you must ship only one package, then you cross join these two, do a cross join. So to get one, it's one very big table that has as many records as the product of these two, but it can be used later to join with a table that's related to either student or exam type. That's why we have this kind of cross join. When you have this operation, the end product is the same as any of the previous products. Yeah. So this, the first one, whatever you get out of the first one is the same as what you get from the cross join, then do the join later. The only downside is that the cross join, there are so many records, but you have to ship them, and it's expensive to ship them. You want to avoid those scenarios. Yes. So you have this table. So this would represent options in the search space. But this is not a query tree. These are like options of a search space. You start at the beginning. You want to order the join such that can have these routes. If you evaluate this one, it gives you a certain cost. Employee joins assignments, and then sorry, let me just erase that. You're trying to generate join ordering. You can go this side where you want to start with employee, and you can either do employee with assignments or employee cross join projects. Okay. Or if you want to start with assignment, you can do assignment join employee or assignment join project. Yes. If you choose this one, for example, you want to start with assignment join employee, then you start with that assignment join employee, and then eventually you join whatever you've joined and gotten projects. Yes, so that you avoid a cross chain. So so these are possible one. The first one is a possible one. This one that other cross join is should not be generated. The one in blue is also a possible one. Assignment joining projects. It's also possible because now you can join those ones with employee. The last one here is not appropriate. So if you want to generate a search space, you can use this as a mechanism to generate your join order. So we say, let me start with employees on the first left branch. The middle branch is where you want to start with assignments as the first one. You want to ship assignments somewhere, right? You can either ship it to, shown in blue, into where employees is. Once you do that, the result you have to ship it to where the project is. That is that. Like now this part, you want to start with assignments. You to ship assignment somewhere. You can ship it either to employees or ship assignments to where projects is. If you follow the right route, follow the right means you want to start shipping projects. So project, you can either ship it to where assignments is or where employees is. If you ship it to where assignments is, it's okay, because now whatever you get from employees, you can ship it to the, whatever you join with assignments, you can ship it to the employees. If you go to the second option of projects cross-join employees, already that is a red flag, because the cross-join is too large. Yeah, then because you know that there are some indexes on the tables, then you can make use of them. Although index now help on the local costs, right? Local costs is what you want to consider. Yeah. So optimizing, full optimizing, you consider local costs, indexes, of course, it's going to be okay. Help you filter your things faster. Yes, then transfer strategies. Do you ship the entire fragment, or do you ship primary keys to do some joins as opposed to all the columns, which is what fetch as needed is. This one you covered in the semi-joins in the query processing slide and recording. Let's assume you use you have two tables you want to ship. There's a master table and there's a child table. You have R, which is the alpha table, and you have S, which is the child table. That kind of relation. R, the R is considered to be half, because it's a one-to-many. You have a few records in R and many records in S. If you are to ship the R to where it's a site of S is, right? You have to ship these ones. So R is here. Ship the entire. So you ship this where S is. What are the costs involved? There's a local cost of fetching R from disk. In our case, we want to assume that this is 0. Then there's a communication cost based on the size of R. Yeah, there's some cost there. It is going to be y is equal to mx, some value, and then based on the size of x, plus some latency. Then there's going to be some local cost of fetching records of S from disk and combining them with the, and you want to fetch as many records as they're in R. Then there's a cost of sending that result to the result site where this data is needed. So for our cost, in the case of a distributed database, we want to focus on these two elements: communication cost of the entire table R and the table that comes out of R and S joint, right? If these two tables are linked and you have 5 records in R and 10 records in S, you're likely to get 10 records being shipped from the site that has S to the decision site. There's another option. Let's assume that you are now shipping the table, the site that has table S, relation S to where R is. We get S from disk. That's a local cost of getting S. Communication cost, we use now Y is equal to MX plus C. And because S is large, S is an inhalation, is a child table, it's going to be a lot of data. You need to store it also in disk. That's a local cost though. Then you fetch R from disk. Then you join them. Then you send them to the decision site. Again, if R has 5 records, this one has 10 records, then they join them, you get 10 records outside. You have this kind of, so the communication cost is 10. If you assume that y is equal to mx plus c, we're saying y is equal to x plus 0. I think the cost is the same as the number of the size of the R. Communication cost from S to where R is 10. Previously, we are moving R to S. Previously, we did this. We moved R to where S is, and then the joint relationship there, 10 records move from S to the decision side, and the other cost of 5 moving table R to where it is. So the cost here is actually 15. But in this second strategy where you're shipping S to R, the total cost is 20. 20 there. Total cost here is 15. So the first strategy is more efficient. There's a third strategy that we can do. We can fetch records of the inner relation for each record of the outer relation. You're saying you have R, yes, you have S, of course, in the decision side. You're saying we rather move the entire table R. You know, R is like this. It has a primary key and lots of other columns. We only want to move this first column as the primary key. Yes, not the entire R. So the size of other is going to not going to be 5. It's going to be a fraction of 5. It might even be a cost of 2 as opposed to 5, because we're only moving one column as opposed to the entire set of columns for each record, right? So there's a cost of local cost of fetching up from disk. Then the communication cost is only sending the primary key, which is A, the column A, which is ID. There are 5 records, yes, there are 5 records, but the actual size is not as big as it was before, because we are only moving a fraction of the relation. Then here, the cost is going to be a fraction of not 10. Yeah, here it's going to be still 10, because we wanted to get the data from S. It's going to be 10. So here in this cost, the cost is 12. So this is the cheapest way. If the query that we had, the query that was coming in was interested in doing a join of R and S with data only from S, it was invoice and invoice details. We wanted to know how many items have been bought so far in the last 1 month. Yeah, so we are only interested in the records from S. Then that's the cost. That's the cost, right? There's also a fourth strategy: move all the relations to a third site. Just ask them to be shipped entirely to the decision site. Then you do the joining there. Here to be 5 and cost here is 10. So cost is 15. Okay, the response time is much faster this way, because everything is being done in parallel, but the communication cost is there. So there's a local cost of getting the table R and also S at the same time. There's the communication of S, and the communication of R. There's the cost of storing S, because assume that S is much bigger than R, so you need to store it, right? And then there's the cost of doing the join. If you have to draw calculate this search pace of ours, the first strategy we got a cost of 15, 5, 10, 15, 20. It was let me draw it much lower. We have to plot those 4 strategies in our search space. The first one, second one, third one, and fourth one. This is 10 and 20. The first one we got 15. The second cost was 20. The third cost was 12. And this fourth cost is 15 still. So our graph is like this. And so these are the four strategies. Yes, on having two tables. If you have to do an exhaustive search, we calculate all this, then we choose the best one, which is the third strategy. Yes, any question so far? So I'll want us to stop here. And next we'll go about the one algorithm for optimization that illustrates what we've just talked about. It's called the hill climbing algorithm. It's one such example that estimates. You'll see it generating one strategy of moving the relations across the site. It starts by having everybody move to one side, then it goes to try to improve that strategy by saying, okay, having everyone send records to the decision site, like the fourth strategy we just seen, is strategy 4. Let's have let's send one relation to a site where there is a related relation, and then see if the cost is improved. Yeah, and it also tries to estimate the intermediate sizes. It tries to estimate the join sizes after the tables have been joined, right? If there's a filter, it tries to estimate the filtering of those records and what happens once filtered records go to a site that is an outer relation or is an inner relation. What comes out of that? So this one is would be a good example to practice what we have just seen in the global query optimization. Okay, so if there are no questions, we can end here.
Excuse me, sir.
Yes.
I'd like to ask. I'd like to speak to you, but it's not related to the unit. I want to talk to you about the email I sent you last. It was on Monday. We spoken last week.
Okay, let me stop the recording for that.